All right, here, let me try a video solution, another one from the hard book, the university book here. And it's not much different than the one that I did a little while ago, number 60. In fact, maybe I would encourage you, before you watch this one, go to number 60. Because they almost ask the same thing. In fact, maybe even a little bit easier. As you see, number 60, we did two beams because we did a red and a green beam, so there was dispersion here. Here we just have one beam. And that being said, this one beam, also, they ask for kind of a different distance, I think. If you looked at number 60, I said the beam came in, it bent, and then, of course, it curved back. This picture, it may not curve back the same amount because we don't go back into the same index we left in. But in number 60, we did, and we showed that the direction of this would be the same as that one coming in. This one would be a little different because, you know, unless these are the same indices, the amount it bends towards the normal doesn't equal the amount it bends away from the normal. So this could be, you know, a beam here that's not parallel to the original direction. So keeping that in mind, let me go ahead and, you know, just focus on what they're after, because in number 60, I calculated kind of this distance. How far apart is the new beam to where the beam was going? And so it's this perpendicular distance. But this problem is asking for the distance kind of on a horizontal of where it emerges compared to there. So it's slightly different because they're asking for a slightly different dimension, unless I misinterpreted number 60. So that's kind of my disqualifier. And I kind of hoping that I didn't, but I got to admit it's easier to do the math across here. So like I said, this is actually probably an easier problem because I don't have two beams and I'm doing a little different geometry, as you'll see. Anyways, let's read the problem here. It says, shown below is a ray of light that goes from the air into from air through crowned glass into water. So it sounds like this is then glass and then water. So maybe this is a sideways view of an aquarium or something. All right. Crown glass into water, such as going into a fish tank. Okay. Calculate the amount the ray is displaced by the glass, so the delta x. Given that the incident angle, so up here, is 40 degrees and the glass is 1 centimeter thick, 1 centimeter thickness. In fact, that 1 centimeter thickness is the same thickness as we had in the other problem here. But we are asking for kind of, like I said, a different dimension here because we did this far apart. So without going back and redoing number 60, thinking maybe they interpreted this, they show it very clear what the delta x is. So I'll keep that in mind. And since I've already drawn in red on here, let me switch to a different color. Maybe I'll save the green a little bit. I'll do a black here because if I draw the thickness here, this length, and then this length, maybe I will call this, say, a distance 1, and then from here out to here, I'll call it a distance 2. But what I'm trying to get you to see then is that D1 plus the delta x is the D2. That is, what we're hunting for is delta x, and I could get that if I get the D2 and the D1. Now, the D2 would be where the light had gone had it not been deviated, had it not refracted as it entered. And the D1 is where it actually does go now that it does refract. And see, the reason that is quite useful is this angle is often referred to as theta 2, and I guess it's right there, and I kind of covered it up. But the angle where it would have gone, had it not deviated, would be theta 1. And so if you kind of look at, here's where I'm going to do the green, this triangle, where the light actually went, you can see that D1 is opposite of it, and we know the thickness of it. So this is a tangent. So I guess I'd write tangent of theta 2 is D1 over the thickness. Whereas if I look at a triangle that has the thickness and then has this D2, kind of making a triangle where the light would have gone had it not refracted, and that would make an angle of theta 1. I can do the same kind of logic and say the tangent of theta 1, okay, is this D2 over the thickness. Okay, and so again, knowing the angles and the thickness, which we know theta 1, it's given, we know the thickness, that's given, that'll easily give us D2. And then D1 we can get after we do Snell's law to figure out what the refracted angle is. So in other words, we can get the D2 and the D1 and then come back and finish up the problem here. So giving myself some room to calculate, I'll do the simpler one first. Tangent of theta 1 is D2 over the thickness. Or solving for D2, it's thickness times the tangent of theta 1. And the thickness, they said, is 1 centimeter, and the incident angle is 40 degrees. So this would be just 1 times the tangent of 40 degrees. All right, so that's about a 0.8, what is that, 39? Maybe I'll just go 39. Well, no, I don't need to be kind of high precision. This is a good distance. Okay, so 0.839. Now, before I can do the other equation, which is the tangent of angle number 2, I knew to apply the Snell's law. So N1 sine theta 1 is equal to N2 times sine theta 2. Okay, so we're starting in the air, so 1.0003 for the index of air. And the incident angle, as they said, is 40 degrees. And we're going into crowned glass. Okay, so I make it very clear. And if I grab the textbook, I'll flip a couple pages, table 1, and scroll down to my solids, and crowned glass is the 1.52. Now, if you remember from the other problem, 1.52 is kind of an averaging effect because they do vary a little bit. Crowned glass on the low end of the scale is 1.51, but on the high end of the scale is 1.53. So kind of in the middle ground is 1.52. So without them telling me what color I have, I'm just going to kind of take the middle of the rainbow, and it's, 1.52, and then sine of theta 2. Okay, so coming over here, 1.0123 times 3 times the sine of 40 degrees. Then I will divide that by 1.52, and then I will take the arc sine and get an angle of about 25.0 degrees. So, again, definitely bent by about 15 degrees because it's coming in at 40, narrows down, and is only at 25. So it's shifted by 15 towards the normal. Okay. All right. So, I can now come back over here and do this D1. So tangent of theta 2 is d1 over the thickness, or the thickness times the tangent of theta 2 is the d1. And the thickness is the 1 centimeter, and we're looking at the tangent of 25 degrees. So I will go tangent of 25 degrees. And so this is 0.466. Okay. And this was all in centimeters. So centimeters, and D2 was in centimeters. Okay, so finally to finish the problem, how much it shifted over is the difference between those. So taking this 839, it's probably just right up here in my calculator. There it is, enter. And subtracting off this last answer, enter, I will get the difference between them as 0.373 centimeters. So almost 4 millimeters. And so the beam is a little shifted from where it was going. All right. Hope that one helped. And actually, now that I think about it, maybe that one is worth watching first, because the harder one is when we got the two beams and we're looking about this perpendicular distance as opposed to the distance along the glass wall. All right. Hope that helps somebody. Take care.